So now let's cover concepts review part number 2, the op amps. And when you do op amps, you normally use a table like this where you have the configurations, the op amp configurations and the respective equations, and you try to match the op amp to this table and then get the equation out of it. But what if you don't have this configuration? So how do you go from there? So it's good to know how to take the expression out of any op amp configuration. And as a quick review, basic assumptions that you can have or you can do is the current flowing through the op amp, the terminals of the op amp, the VP and VN, is equal to 0. And you have also this difference of the voltage going inside of the op amp, the difference between, so VP minus VN is also equal to 0. That's pretty much all you need to know about op amps. Then you have two modes of operation, either comparator mode, no feedback, or amplifier mode, where you have a feedback. Your output is connected to the input somehow. And some other things that we need to know really quick: the output current is generally not known. So normally you don't know the current that is going out unless you apply a load to your circuit. You apply KCL at the inputs of your circuit. So for example, here or here or here, here or here, in order to find the equations. When you are in comparator mode, this difference, this delta V in, is multiplied by a large gain in order to get your V out. So your op amp in comparator mode is going to saturate either to the VCC or ground, or the VPP, if you want to call like that, the negative part, the negative supply of your op amp. And V out is limited by those external power supplies. So let's go over first a couple of examples or exercises. This first one, we want to calculate the V out. So the first thing that we see is we're going to populate the circuit with things that we know. And we know that VP is this terminal over here, and VN is over there. And we know that VP and VN are the same. And by looking here, let me go put a pen. I notice that over here I do have a voltage divider because no current flows in this direction inside of your op amp. Alright, so if that is true, then what we can do is take a voltage division rule here to find VP, and VP is equal to 2 volts. Knowing that I know VP is equal to VN, 2 volts, so now I know the voltage at this point. Now I apply KCL at this point, and what I get is the current I1 plus I2 equals to 0. Remember that the current here is 0, so that's why I don't have it over here. Then I apply Ohm's law. I1 is Vn minus 0 over 2K, and I2 is Vn minus V out over 5K. Solve this equation and I get V out equals to 3.5 times Vn. Multiply Vn by 2, multiply 3.5 by 2, and my V out is equal to 7 volts. So let's use Falstad to validate our answers. And that's what we get here. We get our op amp, the voltage divider. We have here our voltage, 3 volts input. Cool. We have 2 volts on the VP. I can go and measure the VN, 2 volts. So everything works great. All right, let's go back to our presentation and let's move on to the next circuit. The next circuit, we want to calculate the current that comes out of the op amp and the voltage across the 2K ohm resistor. So again, let's populate with what we know. We know that VP is going to be equal to 0, which is going to be equal to Vn. I apply KCL on that node, so I have I1 and I2 coming in, I3 coming out. So VP equals to Vn equals to 0. I1 plus I2 equals to I3. Let's apply Ohm's law, and I get 2 volts minus 0 over 5, 1 volt minus 0 over 2.5K, and 0 minus V out over 10K. And if I solve this equation, V out is equal to minus 8 volts. So that's the voltage that I have across this 2K ohm resistor. Alright, so now I want to find I0. And so I go here and I apply KCL on this point over here. And what I have is I have I0 coming out, coming in, and I3 coming in, and I coming out. Remember, the direction of currents do not matter as long as Ohm's law, you respect Ohm's law. So I0 plus I3 equals to I. So remember, I is V0 over 2K, and I3 is 0 minus V out over 10K. And if I substitute the values, I get a current of minus 4.8 milliamps. So let's see this circuit in action. And here you go. I get close to 0 volts. So I have 0 over here. This is very small, 0 volts. This is my 2 volts. This is my 1 volt. And my output voltage minus 8, and my I0 minus 4.8. So if I hover here, I get a current of, here you go, 0.8 milliamps over here. And this one will be my 4 milliamps of current. So cool. All right, let's move on. Now this one is slightly different. On this exercise, we need to design the amplifier to have a gain of 7.5. Okay, so I want a differential amplifier. Now I use the table from the beginning, and this is the differential amplifier circuit, which has this equation. So now the gain, I know it's R2 over R1, so all I need to do is set up R2 over R1 equals to 7.5. Because I don't have any restrictions on my input resistance, I can pick any value of R1 to get R2. In my case, I'm picking 20k ohms, which gives me an R2 of 150k ohms. All right, cool. So remember, I'm doing V2, which is this one minus that one times the gain. So let's go and simulate this circuit. All right, so I have 2 volts minus 1 gives me 1 volt, and the gain is 7.5, so 1 times 7.5, here you go, that's your output gain. And if I change, let's say, this voltage to 3 volts, then I get 3 minus 1 gives you 2, 2 times 7.5, and you get your 15. Great. All right, next exercise, we have now we start cascading or connecting op amps together, configurations together, and I want to calculate the voltage output on this op amp and the current flowing through this resistor. All right, let's put things that we know. And this configuration, this first configuration, it's a voltage follower or a buffer. So the voltage that I get on my VP shows up on my VN, which is going to be that voltage, 1.2. And the same thing applies for your second op amp. The voltage at the terminal of the VP shows up on the VN, and that's the voltage that I get over there. All right, cool. So now I just need to apply KCL at this node, and I get I0 plus I1. Remember, no current flows up, equals to 0. Apply Ohm law, and I get a V0 of 6 volts. Now the current over here is going to be just applying Ohm's law. I know the voltage over here, I know the resistor. So it's as simple as 1.2 divided by 50k. Let's simulate the circuit. And here, this is what you have. So your output is 6 volts. I get 1.2 volts that shows up over there. So again, so if I pick up these and put it there, that's my voltage. Great. Plug it back again. And my current flowing through the 50k, 24 microamps. So everything is good. Next exercise, we now have 3 op amps connected together, and V1, which is this voltage, is equal to 1 volt, V2 is equal to 2 volts. So the same thing applies here. Let's put things that we know in your circuit. We know 1 volt, 2 volts, and let's go and analyze each block individually. So notice that block A and block B are exactly the same one. They just have different resistors, and block C, it's a different configuration from A and B. So using the table in this case, we can accelerate the process a little bit. A and B are inverting amplifiers, and your C is a summer. All right, so let's find our voltages over here. Let's find the voltage, the output voltage of your block A and the output voltage of your block B. So A will be as simple as applying this equation over here. So R2, 6K over 2K times V1, negative of that, minus 3 volts, and block B is going to be minus 4 volts. Now for block C, I have a summer. I only have 2 inputs instead of 3, so I just rewrite this equation with just 2 inputs. And I know that instead of having V1 and V2, I have VA and VB. And I plug the respective resistors, and your V0 is equal to 8.67 volts. All right, let's see if this is correctly done. So we're going to use the simulator to validate our answers. All right, this is the circuit, block A, block B, block C, and here you go, minus 3 volts, minus 4 volts, and the output 8.66 volts. So our calculations are correct. All right, next problem. We have this configuration. Let's place what we know in a circuit, and what we know is the following. So the first one on the top here, it's a voltage follower, 7 volts, V1 shows up on the negative, shows up over there. I have 3.1 volts on my V2, and I know that I have 0 volts over there because my VP is connected to ground. And I also know that that point is 0 because my VP is connected to ground, which is going to be equal to my VN. I assign current directions, again, assign whatever direction you want. Now let's start by calculating this V0A. So I1 current here is equal to that current I2, apply Ohm's law, and I get V0A. Now I know I have 7 volts and minus 15.5, so I apply KCL on this node, and I get a V0 of 10 volts. All right, let's simulate the circuit. And this is what we have, 7 volts, minus 15.5. If I go here, I have 0 volts. If I go there, I should have 0 volts too. Let me actually put this slightly different here. So if I go there, I get 0 volts. All right, cool. So I'm going to put this one back. And everything is done correctly. All right, our last op amp, probably the most confusing one because we have kind of 2 feedback loops here. We have one over here and another one feeding back over there. Again, no need to freak out. First thing, we put what we know. We know that VP is equal to 0, VN is equal to 0. And now here it's the fun part. We have Vout feeds on your VN, so that point is going to be equal to Vout. And we put current direction, so I1, I2, I3. Remember, I have no current flowing inside of the op amp. And I take KCL, which gives me I1 equals to I2 plus I3. And I get a relationship here between all the voltages present in the circuit. So VA, Vout, and your Vin. But I need to have a voltage gain just depending on V0 over Vi. So I need to remove this VA somehow. So notice here that I can actually find a relationship between VA and Vout on this part of the circuit over here. And if I do that, notice that it's a simple voltage divider. V0 is equal to VA times R4 divided by R3 plus R4. So notice that I can apply a voltage division over here because the impedance on this op amp here is going to be very high, and the impedance of this op amp here, the output impedance, is very low. That's why I can take the voltage division. If I substitute this VA over here, I get this equation, and I'm just substituting here KA by, or R3 plus R4 divided by R4 by KA. So it makes my equations just a little bit easier to see, but that's what you get.